Improper integral has got two more names. It is called infinite integrals or generalized integral. So, first of all, what is the proper integral? Any from integral a to b f x dx is called a proper integral if the lower limit and the upper limit are finite, f x is bounded throughout a b. For example, suppose if we have a curve x o y, and suppose this is the curve y equal to f x, then this is your a, x equal to a, x equal to b. So, this is the a, say 1 2 3 x squared dx, it is a proper integral. Or say integral 0 to 1 sin x upon x dx, this is a proper integral. How? Because you see lower limit and upper limit are finite, function is bounded, you see, because it looks like 0 is a point of singularity, but it is not, because limit sin x upon x, x tends to 0 is 1. So, that is why it is a proper integral. And so, for proper integral we require a and b, both the lower limit and the upper limit should be finite and function should be bounded. So, now what will happen for improper integrals? For improper integrals, while defining, if we let in this integral a to b f x dx, so two possibilities may arise. First possibility is that if your a and b becomes infinite, okay. So, either a or b or both a and b becomes infinite. So, this is one possibility, then we will say it is an improper integral. Another case may be that a and b are finite, but the function becomes unbounded at some point, either at a or b or some point within a b. So, it will be that a and b are finite, but our function f x becomes unbounded or infinite, either at x equal to a or x equal to b or at one or points interior to a and b, or at one or more points within the interval AB, open interval AB. So, these are the two cases. First case is called improper integral of first kind, very important. So, this first case is called the improper integral of first kind. Second case, that is when your a and b are finite, but the function becomes unbounded or infinite, this is called improper integral of second kind. Improper integral of second kind. Okay. So, for this we assume something like, so that our this is defined, this improper integral is defined, we will make some assumptions. What is the first assumption? Because we would like to study systematically, for that we will assume some conditions. The first condition will be that within this interval a to b f x dx, first thing we will assume when you study is that our f x does not change any sign throughout. So, assumptions when we study. So, the first assumption is that the integrand f x does not change sign. Throughout the interval of integration or within the range of integration. Then you will ask that, ma'am, what will happen if it changes sign? Yes, we will come to that point as well. So, when it changes sign we will deal a little later. So, first of all we will deal, or this is the assumption that our function does not change sign. That means, it either stays positive throughout the range of integration or it becomes negative throughout the range of integration, but does not fluctuate or change sign. So, without any loss of generality, we assume that our integrand f x is greater than or equal to 0 throughout the range of integration. Suppose if our f x is negative, then what will happen? Suppose f x is less than equal to 0, then what we will assume? We will assume a new function, say g x is minus of f x. This is how we will define. So, that g x is greater than or equal to 0 throughout the range of integration, and we can start the theorems and everything. Clear? Next assumption which we will undertake is that our function is piecewise continuous. This is the most important thing, that our function f x is piecewise. That is, if we have an interval a b, we have several subintervals, say alpha beta. Our function is continuous within those subintervals. At the endpoint, they should have finite limit. That means, it should not have infinite jump. So, how we will write? So, f x is continuous over each finite subinterval. Okay. Say alpha beta, which is contained in this a b, contained in the range of integration. Okay. Hence, since it is continuous, it is bounded, hence there exists a positive constant k independent of both alpha and beta, such that integral alpha to beta f x dx is less than k, that number k. Improper integrals are evaluated by a limiting process, and simple cases of this improper integral may arise is in the problem of elevation. For example, suppose you have a plane curve and you want to study systematically on improper integral of first kind. What is that? So, that means here range is infinite. Range is infinite, very important. So, first of all you have to classify which improper integral it falls. So, there are three cases here to follow. First case is that you can think about that upper limit is infinite. So, a to infinity f x dx. So, basically what we do, so we evaluate this improper integral by limiting process, because when you have a graph, say this is the curve and you want to find a definite area. So, this is the area below this curve, but if I say find a to infinity, so you will say what do you mean by infinite area. So, infinite area is that we will try to consider the definite part, that is a to b, and then we will take the limit. If the limit exists, we say that is the value of the integral or it converges, and if it does not, then we say it will diverge. So, what we will do, we will try to make it a definite integral. So, it is integral a to p f x dx. So, this is a definite integral or proper integral, and you can apply all the properties of definite integrals, and then we will take the limit p tends to infinity. So, limit p tends to infinity integral a to p f x dx. So, give it equation number 1. So, if this limit exists, if this limit exists and is finite. Suppose this limit exists and is finite, say it is equal to a number say L1, then we say that this improper integral converges and it converges to the number L1. So, then we say that the improper integral converges to the value L1. Otherwise, suppose if your limit does not exist, then we say it diverges. Otherwise, improper integral diverges. Improper integral diverges. So, this is the first case. So, your upper limit is infinite. Second case will be your lower limit is infinite. So, this is the second case. So, here we will change the limits. So, it will be minus infinity to b f x dx. So, what will happen? So, here again our technique is the same, we will try to make it a proper integral first or definite integral. So, what we will do? We will write p to b and p tends to minus infinity, okay, f x dx. Give it equation number 2. So, this is now a definite integral. So, you can apply all the properties of definite integral and then you take the limit. So, this is the technique or this is the trick by which we evaluate improper integral, because you do not know what do you mean by infinite area. So, that concept you do not know. So, we apply it through the limiting procedure. So, if this limit exists and say it is finite, say equal to the number L2, then we say the improper integral converges to the value L2. Otherwise, this integral will diverge. Okay. The third case will be, you can all guess that ma'am, both the limit upper and lower limit becomes infinite. Then what will happen? Yes. So, it is a minus infinity to infinity f x dx. So, both the upper and lower limit are infinite. Then what you do? We will apply a trick. First of all, we will break it up into two integrals. One will be minus infinity to some interior point c. So, where c is some point lying between minus infinity infinity at which the function is defined or bounded. So, we will say a to c and then c to a to c and then c to this b, where this limit a tends to minus infinity and this limit b tends to infinity. Okay. So, this is f x dx and this is also f x dx. Give it equation number 3. So, now we have got two integrals to consider. So, first of all, we will find the limits because both of them are proper integral and then you take the limit. If both the limit exists, then only we say this integral converge. If one of the limit is not convergent, then we say the entire integral will diverge. So, we will write where what is c? C is any point where c is any finite constant including 0. So, this is how we will break it up. So, c is any point within the range and it can be 0 as well. So, here we will check if both the limit exists, say it is equal to L3 and L4. If both the limit converges, then only we say the integral converges. Let me just reiterate, if both the integral converges, then only the main integral will converge. If one or more of the improper integral is not convergent, then we say that the whole integral diverges. So, if one or both the limits do not exist, If one or both, then the improper integral diverges. Okay. Now, we will do some problems regarding this concept. The first problem which I would like to give in this direction is starting with a simple problem, integral 0 to infinity dx upon a square plus x square. A is positive. How will it do? Here you can see quickly that because the range is infinite, it falls in improper integral of first kind. So, first of all you have to classify, when you see a problem you have to classify which form it falls. Then first of all we will make it a proper integral. So, it is 0 to b limit b tends to infinity dx upon a square plus x square. Now, this is a proper integral or definite integral, we know what is the integration. This is just tan inverse 1 by a 1 upon a tan inverse of x by a. So, this is b tends to infinity. So, it will be 1 upon a tan inverse of x upon a, and we will put the limits is from 0 to b. So, this will be equal to limit b tends to infinity, and then we put the limits. So, it is tan inverse of 0 is 0 and this is b upon a. So, this is 1 upon a tan inverse of b upon a. Okay, now we put the limit. So, it is tan inverse of infinity and even that is pi by 2. So, your answer is pi upon twice a. So, this is the answer. So, here we will say that this improper integral converges and it converges to the value pi upon twice a. Similarly, you can do other problems as well. So, some problems I give which you can study and try to do. Suppose we take this problem, integral 1 to infinity dx x root over of x square minus 1. So, here you can see this is upper limit. So, this is actually a problem of mixed kind, that is because of infinite limit it is first kind, and because 1 is also a point of discontinuity, because if you put 1 this becomes 0. So, your function becomes unbounded. So, it falls under mixed kind category. So, this is, so how will you do? You will break it up. So, 1 to c, c to infinity. Okay. So, dx x root over of x square minus 1 dx x root over x square minus 1. So, it is a problem of both first kind and second kind. Second kind will come a little later. So, before that we will do this problem. So, how to do? Here 1 is the point of discontinuity, it is in the lower limit. So, as soon as you put 1 this will become 0. So, the way we will do, we will again try to make it a proper integral. We will add, because it is in the lower limit, it will be 1 plus epsilon. Epsilon is a very small number, it is, but it is positive. Very small number, it is tending to 0, but it is positive. See, dx x root over of x square minus 1. And this is as usual, we will try to make it a proper integral. So, it is limit integral c to b, b tends to infinity dx x root over of x square minus 1. And you know this is nothing but sec inverse of x. So, we will just put the limit and we will get the answer. So, it is limit this sec inverse of x, we will put 1 plus epsilon to c and limit epsilon tends to 0, and that side is also this same. So, it is sec inverse of x c to b and limit b approaching to infinity. So, then you can put the limits. So, it turns out this will be cancelled, few terms will be cancelled. So, this will become so as soon as you put the limit, so it is sec inverse of c, epsilon is 0. So, it will become sec inverse of c minus, if you put the limit, so this will become sec inverse of 1 b and b tends to infinity. So, this will become pi by 2 minus sec inverse of c. So, these two will be cancelled and whatever is left is sec inverse of 1 is 0. So, this will be pi by 2. So, this is the answer. So, we will say that the given improper integral converges to pi by 2. Next, some more problems we can give as an exercise. For example, exercise 1, what will be minus infinity to 0 e to the power x dx. You can say this is minus infinity to the lower limit. So, you have to substitute integral 0 to infinity x sin x dx. You have to apply the product rule, make it a definite. Then integral 0 to infinity e to the power minus ax cos of px dx. A positive, p constant. Next, we come to a very important theorem, which is quite important. Because it is required for solving problems, other problems. So, this is discuss the convergence of the improper integral integral 1 to infinity dx upon x to the power p. So, first of all, again, now this is a very important integral. It is sometimes called the p theorem. So, in solving other problems, complicated problems, you might need to use this result. It is an advantage if you know this. So, what is it? It says what will be the discuss the convergence, means what will be the cases on p so that this integral will converge. So, first of all, again, you will try to make it a proper integral. So, how will you make it? We have, so this integral 1 to infinity dx upon x to the power p, we will make it a proper integral 1 to b, then limit b tends to infinity dx upon x to the power p. So, this part we can calculate separately because we have to investigate on p. So, now integral 1 to b dx upon x to the power p, if I work it out, so it is x to the power minus p, 1 minus p. So, this will become 1 by 1 minus p into x to the power 1 minus p from 1 to b. Now, you can substitute the upper and the lower limit. So, this will become b to the power 1 minus p minus 1 upon 1 minus p. Now, the following cases may appear. Now, you can observe, if my p is greater than 1, then what will happen? If p is greater than 1, so this will become, if you put the limit, so here it will become limit b tends to infinity 1 upon 1 minus p into b to the power 1 minus p minus 1. So, now if I just put the limit, you can see by the following cases can arise. So, this will give me the answer from the first case, if p is greater than, p is less than 1 and p is greater than 1. If p is greater than 1, so what will happen? This will come in the denominator. So, this will become, whole thing will become 0. So, this will become 0. And if it is, if p is less than 1, then what will happen? This will become infinite, because you know, if you put the limit, this will become infinite. So, therefore, I can say the given improper integral converges for p greater than 1 and diverges for p less than 1. Now, the case comes that what will happen if p is equal to 1. If p is equal to 1, remember, we have to do it by direct substitution. So, this is the way we will do that. if p is equal to 1 or for p equal to 1, we have, what do we have? We will put 1 to infinity dx, and p is 1, so it is just x. So, dx upon x is log x. So, this will be limit b tends to infinity. Remember, we have to make it a proper integral. So, it is 1 to b dx upon x, and so dx upon x is log x, and so it is 1 to b limit b tends to infinity. Okay. So, now again you understand, because log of b, so it is infinite, which does not exist. So, this limit does not exist, and because this limit does not exist, so the integral is divergent for p greater than 1. So, hence to sum up, for this integral it will converge if p is greater than 1. So, this integral is convergent for p greater than 1, divergent for p less than equal to 1. You have to remember. Okay? And if it is convergent, so it converges to the value 1 by p minus 1. This is the value it will converge. Converges to 1 upon p minus 1. So, take down some problems relating to this. For example, discuss the convergence of the improper integral minus infinity to infinity x e to the power minus x square dx. You can try to do this problem at home. Now the thing is, not every integral, improper integral, can be evaluated like this. There are many improper integrals arising in many practical situations which cannot be exactly evaluated. So, it is enough if we can just comment on the convergence or divergence of those integrals. For example, a simple example can be 0 to infinity e to the power minus x squared dx. It looks like a simple integral, but we do not know how to integrate it because of this x square coefficient. So, what we can do, we can comment on the convergence or divergence of those integrals, and it is enough sometimes just to know whether my integral is convergent or divergent. So, the first theorem in this direction is the comparison test. Comparison test 1. What is this test? It says that if you have two functions f(x) and g(x), as the name says, it is comparison. So, we are comparing. So, it is 0 less than equal to, so both are positive, we have already assumed, and less than equal to gx. So, your one function is less than equal to gx. You have to show this inequality for all x. Then comparison theorem says that number 1, integral a to infinity f(x) dx converges if integral a to infinity gx dx converges. How to remember? You can just think about one function, another function. So, it is f(x) and gx. So, if the bigger one converges, then the smaller one has to converge. And for divergent, if the smaller one diverges, then the bigger one will automatically diverge. So, that means, to write it, integral a to infinity gx dx diverges if the smaller integral, that is the integral a to infinity f(x) dx diverges. Maybe you can look up in the book for the proofs of it, so that you can have a good understanding of this topic. So, this is called the comparison test. This is valid for positive functions. So, we have already assumed that the functions are positive. So, once again, just to reiterate, if the bigger one converges, bigger function, then the smaller one will automatically converge. If the smaller one diverges, the bigger one will diverge. Next comes comparison test 2. Both the tests are important. Sometimes the problem can be done easily by one test or the other. So, theorem 2, comparison test 2. What is it? It says, suppose that f(x) and g(x) are positive functions, and let, we will take the ratio. So, f(x) upon gx. So, this are, remember both are positive, so it is fine, you can do that. Limit x tends to infinity. If we take this ratio and then take the limit, then this will give me a number L, say some number L. What is the restriction? L should lie between 0 and infinity strictly. If L is equal to 0 or it is infinity, then this theorem fails. Then it will be interesting to think about what will happen if L is 0 and L is infinity. Okay. So, try to think about that. So, give it equation number 1. So, once again this is the comparison test 2, you take the ratio, take the limit, this is some finite number L, if it is some finite number L except 0 and infinity, then what will happen? Then we can say that both the improper integral converges or diverges together. This is very powerful and very useful for practical purposes, better than the first one in some cases. Then the improper integrals 0 to infinity, that is a to infinity, f(x) dx and a to infinity gx dx both converges or diverges together. Both converges or diverges together. Okay. Let us do some problem in this based on these theorems. Question: discuss the convergence of the following improper integrals. First one, say we will try to solve 1 to infinity e to the power minus x square dx, the integral which we do not know how to do convergence and divergence. So, this we will now show with the help of the theorem. Another problem we can take up is integral 1 to infinity dx upon e to the power minus x plus 1 into x square. Number 3, which you can try at home, is integral 2 to infinity dx upon log x. Try to do all the problems by both the comparison tests and see which one is better. Solution 1. So, we will try to do this. So, first of all, this is the range, x is lying between 1 to infinity. So, x is positive. So, we know the relation is x square is greater than or equal to x for all x greater than equal to 1. That means minus x square will be less than equal to minus x. That means e to the power minus x square will be less than equal to e to the power minus x for all x greater than equal to 1. So, this is the trick. This is your function gx. If you remember, fx less than equal to gx. So, this gx is in our hand. We can choose it as simple as we can, so that we can easily integrate. So, remember, this is the trick. You should be able to choose or do some back calculation to make sure that this gx is a function which you can easily integrate. So, you can comment whether it converges or diverges. So, in this case I have taken e to the power minus x, because I know it is a very simple integral and I can integrate and I can see whether it is convergent or divergent. Now, the trick is I will integrate first this integral and then see whether it converges or diverges. If it converges, the main integral will also converge automatically. If it diverges, that will also diverge. So, this integral 1 to infinity e to the power minus x squared dx. Minus x dx. So, this one we will consider. So, if the theorem says if the bigger one converges, the smaller one will converge, but for divergence you have to show the other inequality. So, this will be first of all we try to make it a proper integral. So, it is integral 1 to b e to the power minus x dx limit b tends to infinity, and then you know what is the integral. It is just integral minus of e to the power minus x. So, if you put the limit, it will come out to be 1 upon e. So, it is convergent, and this integral is converging to the exact value 1 upon e. So, by comparison test, I can say that this big integral, that is e to the power minus x square, which we do not know what it will be, that will also converge, and it is bounded by this value 1 upon e. Cannot be bigger than this number. So, to write it, we will say so we can say, so this integral is convergent. So, which is convergent? And so, by comparison test, so you have to say which test you are using, very important, so that you understand, and why you are using. By comparison test, test 1. So, this is important, or if you have time you can just mention what is the test. The given integral that is it is integral 1 to infinity e to the power minus x squared dx is also convergent. Not only that, its value is less than or equal to 1 upon e. Further, we can add, although we do not know what is the exact value, we can say that it cannot be more than 1 upon e. Further, its value is less than 1 upon e. That is how we can do. Next problem, that is if we take up this problem, I will try to do by comparison test 2, and you can try to do it by first and then see which one is better or is convenient for you. Next problem, that is integral 1 to infinity dx upon e to the power minus x plus 1 into x square. If I try to do it by this ratio theorem, then what will happen? You can see easily that this is there, x square is there. So, if I take my gx to be x square or 1 upon x square, then something I can comment, but I have to make sure if I use comparison test 2, my limit should not be 0 or infinity. So, let us try. So, I will say let fx be the function 1 upon e to the power minus x plus 1 into x square, and see gx, which is in our hand, we can take it to be as simple as we like, and we can construct it. It is a 1 upon x square. So, therefore, if I take the ratio fx upon gx, so what will happen? You can see this x square will be cancelled, So, it is this is the limit x tends to infinity. So, limit x tends to infinity according to our comparison test. So, this is the function f x 1 by e to the power minus x plus 1 into x square, and if we just reverse it, so it is x square. X is approaching infinity, so not yet reached. So, you can cancel x square. So, whatever is left is limit x tends to infinity 1 upon e to the power minus x plus 1. So, if you put infinity, so this term is 0. So, 1 by 1 is 1. 1 is the limit. So, we are fine. That is because L is a number. So, L is here 1, which is a number lying between 0 and infinity. So, we can now comment. So, again this is in our hand, because we know already what will be the value of this integral by this p test, which I have done a little earlier. So, what we can say again also integral 1 to infinity gx dx, that is integral 1 to infinity gx is 1 upon x square. So, dx upon x square according to our p theorem, because 2 is greater than 1. So, this will diverge, this will converge. So, what will happen? So, I can say this integral converges because p is greater than 1. So, here p is 2, as p equal to 2 greater than 1, and we can see converges to which value? Converges to the value 1 by 1 minus p. So, it will be converges to 1. So, this is the convergent integral. Hence, by a ratio test I can say our given integral this, which is otherwise quite difficult to calculate, is also convergent. So, therefore, by comparison test, you have to mention what is the test? Comparison test to the given improper integral, improper integral, that is 1 to infinity dx upon e to the power minus x plus 1 into x square. This given integral, improper integral, also converges, is also convergent, because our gx is convergent, and moreover its value is less than 1. Its value is less than 1. Okay. Next, we move on to some other problems. Take down some more problems which you can practice at your home. Exercise integral 2 to infinity dx x times log x to the power p. You have to discuss the convergence. Here you have to do by substitution. You have to substitute. Say log x is equal to t. Next problem you can take up. Exercise 2, integral 1 to infinity x tan inverse of x root over of 4 plus x cube dx. Okay. So, it is x tan inverse of x root over of 4 plus x cube. So, you have to again do by substitution, okay, or you can do by ratio test, that is the comparison test 2. Next, we will move to improper integral of second kind, how to deal with that. So, next topic will be improper integral of second kind. Again, we will study them systematically so that it comes to our hand. So, again I told you for second kind our range is finite, but function becomes unbounded at some point. So here a b are finite, that is the lower and the upper limit of this integral a to b f x dx. Here both the limits are finite, but function has infinite discontinuity. So, this is the more interesting case. So, and has infinite discontinuity or becomes infinite at number 1 lower limit x equal to a. Suppose you substitute x equal to a in the integral, function becomes infinite. Number 2 x equal to b, if you put it in the upper limit, function becomes unbounded. Number 3 x equal to a and x equal to b. Say both the limits, if you substitute, it will become infinite. Or the fourth case will be that if you take some interior point c lying within the range of integration, if you substitute c, function becomes unbounded or infinite. X equal to c, where a less than c less than b. Remember, you have to approach systematically, otherwise it will not come to your hand. So, the way we are showing you have to do that, where f x has an infinite discontinuity. So, x equal to c. So, here f x is continuous at or continuous in the interval a b except at x equal to c, where c is the interior point, where function has an infinite discontinuity. Infinite discontinuity. So, remember, for the second kind there are 4 cases, either at the lower limit, upper limit, both the limits, or at some interior points. Function becomes unbounded. Suppose your function has a finite number of discontinuity. For the infinite case, we will not deal here. You have to go for higher order, higher mathematics. So, suppose we are assuming function has a finite number of discontinuity. If f x has a finite number of points of discontinuity, say C1, C2 up till 3 dots, to show there are many points, because in maths we have certain symbols. So, 3 points or 3 dots will show there are infinite number of points between Cn. So, suppose your function has a finite number of discontinuities, say C1, C2 up to Cn, where all are interior points, where a less than C1 or less than equal to C1, less C2, less C3, 3 dots, Cm less than b or less than equal to b. So, here we are dealing with, remember, with finite number of discontinuity. If it is infinite number of discontinuity, we have to go to higher mathematics, not here. This topic cannot handle this. So, if it is the case, then how will you do? So, integral a to b f x dx. If I want to evaluate this integral, so we will break it up, integral a to c1, c1 to c2, c2 to c3, 3 dots to show other integrals are there in between, and last 2 integrals say cm to b. This is how we will do, where all c1, c2 up to cm are the discontinuous points, but finite. So, f x dx, this is the integrand, f x dx, f x dx. Okay. So, this is the discontinuity. Now, we will study, and we have to consider each integral separately, find out whether they are convergent or not, before we comment on the main integral, that is integral a to b f x dx. Now, let us deal with the cases separately. First case, which is very important, is number 1. So, our integrand is integral a to b f x dx. Again, we will evaluate it by a limiting procedure, and we will make it a definite integral. So, in infinite discontinuity at x equal to a. So, how will you do it? So, first of all, remember what you will do. So, it is integral a to b f x dx. If I put x equal to a here, function becomes unbounded or discontinuous. So, what I will do, I will try to make it a continuous. So, the way we will do it is, if it is in the lower limit, we add plus epsilon. Again, it is a matter of convention, someone can say minus also, but we will follow plus f x dx. Generally, if it is in the lower limit, we add plus epsilon. What is epsilon? So, it shows that this function is continuous everywhere except at the point a. That means, if we start from here, so it is a, then a plus epsilon to b, all those points function is continuous, and epsilon is a very small quantity, but positive. So, limit epsilon tends to 0. So, this integral is now a proper integral. You can apply all the properties and then take the limit epsilon tends to 0. Again, just like before, if it exists and has some value, then we say this given integral is convergent, and it converges to exactly that value. So, the integral this is a proper integral. So, where this integral, where integral a plus epsilon to b f x dx is a proper or definite integral, is a proper integral, that is function is bounded and limits are finite, no problem in there, and exists for every epsilon where epsilon range is, epsilon is very small but positive and strictly less than b minus a, because if it is equal to b minus a, then it will just become a point. So, this is a proper integral, and now if we evaluate it, suppose it has the value, say some value, say it is say L1. So, if this limit exists, we say this our given integral is convergent and it converges to that value. Otherwise, the given integral diverges. Remember, we are dealing with infinite cases here. Otherwise, the improper integral diverges, just like before, diverges. Next case comes, suppose you have an infinite discontinuity at the upper limit x equal to b, then what will happen? So, again it becomes a to b f x dx. Okay, so, it is limit epsilon tends to 0 a to b. Now, remember, if it is in the upper limit, we use minus sign. Again, it is a matter of convention. Some books you will see they will do the reverse, but generally we will follow this assumption. If it is in the upper limit, you will give a minus sign, b minus epsilon. Okay, where the improper integral, where this a to b minus epsilon f x dx is a proper integral. Again, if it converges to the value say L2, then we will say this whole integral is convergent and it converges to L2 number, which is finite. Or otherwise, we will say that the improper integral diverges. Third case, if it has a discontinuity at both the limits a and b, then what will happen? So, infinite discontinuity at x equal to a and x equal to b. So, that means if you substitute x equal to a and x equal to b, then our function or integrand f x becomes unbounded. So, here what we will do, we will write integral a to b f x dx. Here at both the limits function becomes unbounded. So, we will separate it into two integrals, say a to alpha and alpha to b f x dx. so that we can study the singularities or the discontinuous points properly. What is alpha? Where alpha is any finite number lying between a and b, but at that point function is bounded, where alpha is any finite constant, alpha is any finite constant between a and b, at which f or fx, a function fx or integrand fx is defined. Now, we will evaluate these two improper integrals. So, how will you evaluate it? So, we will write them as, now epsilon limit epsilon tends to 0. So, this is in the lower limit. So, it will become a plus epsilon to alpha fx dx, plus again this is at the upper limit. So, it will be limit, generally we do not take the same epsilon, because we want to study the singularities from both left and right. Okay. So, this will be say xi, xi is a Greek letter or any number you can give, alpha to b minus xi fx dx. If you take the same epsilon, then sometimes you may not see what is the true picture, because it is infinite, we do not know where is infinity. So, it is very important to study the singularities separately to know actually what is happening. So, next, if both the integrals exist independently, say both of them are equal to say L3 and L4, both are finite. So, together they have to exist. If both the integral exist separately, then we say our given improper integral converges, and it converges to this number. If one of the integral or both the integrals do not exist, or the limit does not exist, then we say it diverges. So, for divergence, if you can show at least one of the integral is not converging, then it is enough to comment on the divergence. So, otherwise it diverges. So, for convergence, I repeat, it has to exist for both the integral, but for divergence, if at least one integral we can show it does not exist, then the entire integral will collapse. Next, the fourth case. The fourth, that is the infinite discontinuity at an interior point x equal to c, where a less c less b. So, what will happen? Now, if you put this point, then the function becomes unbounded. We write the improper integral a to b fx dx equal to, again we will separate into two integrals. So, at the interior point, so we have to study this interior point from both sides, left and right. So, what we will do? We will write a to c and c to b, so as to see what is the true picture going on. So, a to c fx dx, it is still an improper integral. Now, we will try to evaluate it by making it a definite integral or proper integral. So, how will you do that? So, so c is the point. So, it is the upper limit c minus epsilon. Okay. So, it is the singularity basically we are studying. So, this is c and this is the neighboring point c minus epsilon, c plus epsilon. So, we are studying this singularity from both sides, left and right. So, c minus epsilon fx dx, limit epsilon tends to 0, plus again. So, this c is in the lower limit. So, it is c minus or c plus, because in the lower limit c plus is zeta. Generally, we do not put the same epsilon, because they both may approach 0 separately or independently. So, right. So, this to be fx dx, limit xi tends to 0. Again, if both the integral converges and it converges to the value L5 plus L6, both of them are finite, say, then we will say that the given improper integral is convergent and it converges to this number. If one of the integral or both the integrals diverges, then this given integral will diverge. So, therefore, otherwise it will diverge, otherwise it will diverge. So, just to reiterate, for divergence we may not have to show both the integrals. If one of the integral does not exist, then we can just say that it does not exist. In this case, we cannot find what is the value of this integral, but we can at least comment what is the upper bound. So, next we will give some comparison test. Next comes comparison test, theorem 3, comparison test. Just like improper integral of first kind, we have a comparison test 3. What is it? If 0 less than equal to f(x) less than equal to gx for all x in AB, then we will say number 1, integral a to b f(x) dx converges if integral a to b gx dx converges. Okay. Next, number 2, integral a to b gx dx diverges if integral a to b f(x) dx diverges. The reasoning is the same, but it will be good if you can look it up at the proof, if you can see the proof in some book. So, what is it? Again same thing. If we think about these two functions, say this is your f(x) and this is your gx, it says that if the bigger function converges, then the smaller function will automatically converge. And for divergence, if the smaller one diverges, then the bigger one will diverge. So, remember, to show divergence, it is the opposite, you have to remember. That is, if the smaller one diverges, then the bigger function will automatically diverge. So, remember to do that. Next, we will go for comparison test 4. Again, it is just like the ratio test. So, both are equivalent. You can try to show the equivalence. If f(x) and gx are two functions, it is a matter of convenience which one you want to use. For certain kind of problem, you will see comparison test 3 is much more easier. For certain types of problem, comparison test 4 is much better, depending on the problem. If f(x) and gx are two functions, are two positive functions. So, here we have assume everything we are doing for positive. If it is a negative function, then you just define it to be another function gx, which is equal to minus of f(x). So, if f(x) and gx are two positive functions, and number 1, a is a point of discontinuity, point of infinite discontinuity, is a point of infinite discontinuity such that limit f(x) upon gx. Now, remember, a is in the lower limit. So, it is x tends to a plus. So, remember, we take the lower limit plus and the upper limit minus. So, this is equal to limit h tends to 0 f of a plus h and g of a plus h. If you like, you can also give epsilon, no problem. and so say this limit exists and is equal to say L1, some finite number, but L1 should be a number which is lying strictly between 0 and infinity. It will be interesting to find out what will happen if L1 is exactly equal to 0 or infinity. Then this theorem will not hold, but some special cases may be commented. So, that may be taken as an exercise and work out. Next case can be case 2, that if B is a point of infinite discontinuity, such that what will happen if B is a point of infinite discontinuity, then we will take the ratio fx upon gx just like before, but remember here B is in the upper limit. So, this will be limit according to our convention x tends to B minus, that is from the left side you will be seeing it or studying it. So, this will be again limit h tends to 0 or epsilon tends to 0 you can take. So, it will be f of B minus h upon g of B minus h. Suppose this limit exists and is equal to some number L2, where L2 is a number lying strictly between 0 and infinity. Then we can say that both the improper integrals, that is a to b fx dx and a to b gx dx, will both converge or diverge together. So, then both the improper integrals, integral a to b fx dx and integral a to b gx dx converge or diverge together. This is a very beautiful theorem, or diverge together. So, we can comment about their convergence and divergence together. So, basically you have to think if you want to apply this. So, here you have to take gx to be a simple function which you know how to integrate, or you can comment on its convergence and divergence. That is the trick you have to remember, and you have to choose it such that this L2 is not a number either 0 or infinity. If it is 0 or infinity, this test will fail. So, you have to find out what happens then. This will be good exercise. Let us do some problems based on these two theorems, that is comparison test 3 and 4. So, let us first do a problem which we can exactly evaluate. So, evaluate integral 0 to 4 dx upon root x. So, this is a simple integral, you can integrate and you can exactly evaluate. You can see 0 is the point of infinite discontinuity, that is if you put x equal to 0, function will become infinite, it will jump to infinity. So, what we will do, we will try to make it a proper integral. You can see 0 is in the lower limit, so we will add epsilon here. So, 0 plus epsilon is epsilon to 4 dx upon root x, that is we try to make it a proper integral. Once it is a proper or definite, we can do anything we like, and then take limit epsilon tends to 0. So, whenever we say find the area of this infinite integral, we mean actually you do it by limit procedure. So, this is now if you just evaluate this definite integral, so it is dx upon root x is nothing but 2 root x. So, if you work it down, it will come out as 2 will just go outside. So, epsilon tends to 0, this will become 2 minus root epsilon, and if you just work it out, so this will become 4. Okay. So, therefore, the improper integral converges to this number 4. Therefore, the improper integral converges to 4. But as I told you all before, that not all integrals can be evaluated just like so simply. So, for some complicated improper integrals, it is enough if we can comment on the convergence or divergence. So, the next few problems we will do will be based on that. So, before that, we will do one more problem which we can exactly evaluate. So, just take one more example. So, into -1 to +1 root over of 1 plus x upon 1 minus x dx. Okay, so this way, now how will you proceed? You can see 1 is the point of infinite discontinuity. If you put x equal to 1, this will become undefined. Okay. So, what we will do, if you, we will try to take it, let f x is equal to root over of 1 plus x upon 1 minus x. Then you will try to rationalize it. If you rationalize it, so it will become 1 plus x 1 minus x square. Next, if you try to find the integral, so it is integral f x dx. So, it will be integral 1 plus x 1 minus x square dx. So, this will be, if you work it out, so this will become sine inverse x, because you will separate it out. It will be root over. So, root over, so sine inverse x minus root over of 1 minus x square, if you work it out. Next, if you put it in the limit, so this will become, therefore, I is equal to integral -1 to 1 this value. So, this will become 1 plus x upon root over of 1 minus x square dx. So, this will be, if you do it properly, this will come out to be pi. Take down some exercises. Evaluate the improper integral, integral 0 to 3 dx 3x minus x square. You can easily see that x equal to 0 and x equal to 3 are points of infinite discontinuity. If you put x equal to 0, function becomes unbounded. If you put x equal to 3, then this is all 9, this is also 9. So, this will become unbounded. So, how will you do? You will just separate it into two integrals. So, it has got infinite discontinuity at both lower limit and upper limit. So, you break it to some interior point, where at the point C function is defined. So, it will be dx upon 3x minus x square dx upon 3x minus x square. And then you can do partial fractions and you can solve it out, make it a proper integral. You will see that this integral diverges. Okay, so try to do that. So, basically that means up till so far what we have done, it suggests that whenever we say a to b f x dx, so we say it is a limit. If a is the point of a discontinuity, it is integral a plus epsilon to b f x dx. Epsilon tends to 0. That is, we study the singularity from the along the right side. And if we say a to b f x dx, suppose your function is unbounded at b, then you write it as integral a to b minus epsilon f x dx. Limit epsilon tends to 0, that means we are studying the singularity at the point b from the left side. So, that is why these two integrals are important. And when we break it up to both parts, that means we want to study the singularity at the same point from both the sides, left and right. Another example, say integral -1 to 1 dx upon x square. How you will try to work it out? You can see this integral has a infinite discontinuity at x equal to 0, which is interior or within this range of integration -1 to 1. So, better to write this integral, the given integrand has infinite discontinuity at x equal to 0 and which lies within the range of integration, which lies inside inside the interval of integration. Okay. So, because it is interior point, so we will break it into two separate integrals. So, therefore, integral -1 to 1 dx by x square, if I separate it down, so it will be plus. So, this is two integrals, we will separate. So, 0 is the point of infinite discontinuity. So, it is -1 to 0, 0 to 1 dx upon x square, dx upon x square. So, 0 is the point of infinite discontinuity. So, we will write it up. So, this will be -1 to 0 minus epsilon or so it is better to say minus epsilon dx upon x square, limit epsilon tends to 0, plus here 0 is in the lower limit. So, it will become some xi, limit xi tends to 0. Remember, we use two different notations so as to study the singularity properly. Xi to 1 dx upon x square. Now, you know integration dx upon x square is nothing but -1 upon x. So, this will become if we put the limits. So, it is limit epsilon tends to 0 -1 upon x. So, this will be, if we work it out, it is 1 upon epsilon minus 1 plus limit xi tends to 0, 1 upon xi minus 1. Again, you see, if you substitute epsilon equal to 0, this will become infinite, this will become infinite. So, which diverges or does not exist. Okay. So, if I just draw a rough sketch, because you know this is a very important graph. So, it is this is the graph y equal to 1 upon x square. So, this is the area you want to know, this is the point 0, and so this is somewhere say -1 and this is somewhere say 1. Your graph is y equal to 1 upon x square, this is your x and this is your y. So, you see the area actually it is diverging off. But suppose if we do not study the singularity properly, and what you did as soon as you get it and you try to work it out, so what will happen? So, you will just say -1 upon x, -1 to 1. Okay. So, this will minus will be coming up. So, it is 1 upon x -1 to 1. So, this is 1 then plus 1. So, it is -2. So, integral is converging. So, it is a utterly wrong thing, because this function is not bounded. So, you got to consider the singularities from both the sides. But if we do not consider, then we are getting an utterly wrong answer. It is coming out to be converging, which is wrong. So, it is very important to consider the singularities to see what is going on inside. So, take down few more problems in this direction. Exercise. Evaluate integral 0 to 3 dx x squared minus 36 plus 2. If you do factorize it, you can see it becomes dx x minus 1 into x minus 2. You can see both the points 1 and 2, which lies within the range of integration, function becomes unbounded. So, here you have to separate it out. So, how will you do that? 0 to 1, 1 to 2, 2 to 3. All three integrals you have to study separately, I1, I2, I3. You will observe that the middle integral is negative throughout. So, you have to redefine it as a new function gx, which is equal to minus of fx. So, try to do this problem. Next, just like improper integral of first kind, in second kind also we have a P theorem, which is very important to solve other complicated problems. You can state this theorem. What is it? Discuss the convergence of the improper integral a to b dx x minus a to the power p, p positive. So, here you can see discontinuity is at the lower limit. Similarly, we can have a p theorem when your discontinuity will be in the upper limit, say it is b minus x to the power p, then what will happen? So, solution it is also called p theorem for second kind, when discontinuity point of discontinuity is at the lower limit. So, this integral has infinite discontinuity at x equal to a, that is the lower limit. We write integral a to b dx x minus a to the power p. So, first of all we will convert it to a proper integral. So, it will be a plus epsilon to b dx x minus a to the power p, and then limit epsilon tends to 0. And next is the proper integral. So, we can work it out. So, it is d of x minus 1. So, it will become 1 upon 1 minus p will come out if we do the integration, epsilon tends to 0. So, this will become 1 upon b minus a to the power p minus 1 minus 1 by epsilon to the power p minus 1. Okay, once you do the integration. So, here again values of p will come. If p is less than 1, what will happen? If p is greater than 1, what will happen? So, it turns out that if p is less than 1, it will have a finite value, because here p is less than 1. So, say half or something, then so this will become 1 upon 1 minus p times b minus a to the power p minus 1 if p is less than 1, and infinity if p is greater than 1. If p is greater than 1, so this will become, if we put the limit. Okay. So, here in this case it is the reverse. So, it will converge if p is less than 1, diverge if p is greater than 1. But if p equal to 1, again we get it by direct substitution. So, if p equal to 1, we will substitute it. So, at p equal to 1, for p equal to 1, we get by direct substitution what we will get. So, it is integral a to b dx upon x minus a. P is 1 here. So, that is nothing but log will come. So, it is first we will make it a proper integral. So, it is a plus epsilon to b dx upon x minus a, limit epsilon tends to 0. So, this will be log. So, it is log of b minus a upon epsilon, limit epsilon tends to 0. So, you can see that this will diverge. So, this becomes infinity. Okay. So, it turns out that it is convergent for p less than 1 and divergent for p greater than or equal to 1. If it is a convergence, so it converges to this value 1 by 1 minus p into b minus a to the power p minus 1. So, remember, for improper integral of second kind, it will converge for p less than 1 and diverge for p greater than or equal to 1. Let us do a problem. Exercise. Show that the improper integral minus pi by 2 to pi by 2 tan x dx is divergent. As you can observe, this integrand has a discontinuity at the point pi by 2 and minus pi by 2. The integrand has infinite discontinuity. So, you have to first investigate what is the infinity, what kind of infinity it is. Has infinite discontinuity at x equal to plus minus pi upon 2. We have to investigate. Then, because your infinite points are at the upper and lower limit, so you have to separate into a interior point. So, therefore, integral minus pi by 2 to pi by 2 tan x dx is equal to, we will separate it out to two integrals, minus pi by 2 to c and c to pi by 2. So, it will be this plus epsilon, limit epsilon tends to 0, tan x dx, and this will be again pi by 2 minus say some xi, limit xi tends to 0, tan x dx. Now, you know that integration of tan x dx is log of sec x, or a log of a cos log of a sec x, or minus of log of cos x. So, if we just do that, so what will it come out to be? Let us see. So, this if we work it out, so it will be limit epsilon tends to 0, this will become minus of log of cos x, and our limits are minus pi by 2 plus epsilon to c, plus limit xi tends to 0 minus of log of cos x, and if you put the limits, so this will become c to pi by 2 minus of xi. Okay. Now, if we just expand, that is substitute the upper and the lower limit, so this will become limit epsilon tends to 0. So, because it is minus sign, so lower limit will be first, then the upper limit. So, this will become log of cos of minus pi by 2 plus epsilon minus of log of cos c. Okay. Minus the other part, it will also again come. So, this will become minus of limit xi tends to 0 log of cos of pi by 2 minus of xi minus log of cos of c. Now, you can see if you substitute epsilon tends to 0, so then this is nothing, this limit will not exist. So, both the limit diverges. Therefore, the given improper integral will also diverge. If I want to draw the graph, so it is tan x, so between minus pi by 2 to pi by 2, so something like that, tan 0 is 0. So, it is minus pi by 2 to pi by 2. So, this is the graph y equal to tan x. So, this is the area. So, you can see it is actually diverging. Okay. But if we do not separate it out into two separate integrals, what will happen? Let me show you. Note, if we write minus pi by 2 to pi by 2 tan x dx to be limit epsilon tends to 0 and say minus pi by 2 plus epsilon to pi by 2 minus epsilon tan x dx, then what will happen? So, this is nothing but integration of at n x is log of sec x. So, it is log of sec x limit epsilon tends to 0 minus pi by 2 plus epsilon to pi by 2 minus epsilon. Okay, so next we will substitute. So, this will become limit epsilon tends to 0 log of sec of pi by 2 minus epsilon minus log of sec of pi by 2 minus pi by 2 plus epsilon. So, this will become limit epsilon tends to 0. So, this will become 90 minus epsilon is cosec. So, it will be log of cosec x minus log of cosec x cosec epsilon, it will be epsilon. So, both will be cancelled and so answer is 0, but which is utterly wrong. This is a wrong method. So, it is very important that we separate out the integrals. Why? Because here we did not get a chance to put the limit. Without putting the limit, we have cancelled it. So, it is a utterly wrong method. So, it is very important that we separate into two different integrals and study the singularity properly. Next, we will try to do some problems on the comparison test 3 and 4. So, take the problem, discuss the convergence of the following improper integral. Number 1, say integral 1 to 2 root x upon log x dx. So, we will apply the comparison test. So, what we will do, how to do we will show. We have f x is equal to root x upon log x. Both are positive because your range is from 1 to 2. So, x is lying from 1 to 2, same sign, positive. Here x equal to 1 is the only point of discontinuity. So, the point x equal to 1 is the only point, like this we have to write, is the only point of infinite discontinuity. Let gx, which is in our hand, we can choose it to be a simple function which we can easily integrate and comment. Gx is, say I am taking x log x, just I have to make sure that it is not a number either 0 or infinity. Then we have we will take the ratio f x upon g x limit x tends to 1 plus, because 1 is in the lower limit, and according to the formula it is limit h tends to 0 or epsilon, also you can give any number, f of 1 plus h, g of 1 plus h. So, if you substitute, so g of 1 plus h will be, x will be replaced by 1 plus h. So, 1 plus h into log of 1 plus h. So, if you substitute, so this will become limit h tends to 0, f x is root x. So, it is root over of 1 plus h upon log of 1 plus h times. So, g x it will be x, that is 1 plus h, x will be replaced by 1 plus h, log also, log of x will be replaced by 1 plus h. So, now log can be cancelled because h is a number which is approaching 0, it has not yet reached 0. So, we can cancel it out. So, this will become limit h tends to 0 1 plus h to the power 3 by 2. If you substitute h equal to 0, so it will become 1. That is, we have got a finite number which is neither 0 nor infinity. So, we can say that both the integral will either converge or diverge together. So, now I have to see what about g x, whether it will converge or diverge. If my g x converges, then my given integral f x will also converge, otherwise they will diverge. So, therefore, both the integrals integral 1 to 2 f x dx and integral 1 to 2 g x dx converge or diverge together. Now, we have to check what about g x, whether it will converge or not. Now, integral 1 to 2 g x dx, that is integral 1 to 2 dx upon x log x. Remember, we have choose dx to be gx to be x log x. So, this will be again 1 is the point of infinite discontinuity because log of 1 is 0. So, in the denominator we have 0. So, this will be limit epsilon tends to 0 integral 1 plus epsilon to 2 dx upon x log x. So, now if we integrate, so it is by substitution you can do. So, it will become log of log x. So, by substitution we will get, so which is equal to limit epsilon tends to 0 log of log x, and our limits are 1 plus epsilon to 2. So, now if I substitute the limit, so this will become a limit epsilon tends to 0, upper limit is 2. So, it will become log of 2 minus this log of 1 plus epsilon. Again, if you put epsilon tends to 0 or epsilon equal to 0, what will become? This will become log 1 is 0, and so log 0 is undefined. So, this will again diverge. So, because this is divergent, so by comparison test 4, my integral f x dx will also diverge, because we already said both the integrals will converge or diverge together. So, if I can show one integral is a convergent, other integral will automatically converge or diverge. So, in this case our integral is diverging, therefore, integral 1 to 2 g x dx is divergent, and because it is divergent, so the given integral, therefore, the given integral integral 1 to 2 f x dx is divergent. By comparison test 4, we have to mention the test, comparison test 4, or if we have time, you can just write what is the test and you can mention. Take down some problems similar to this. So, by comparison test 4, it says that both the integrals will converge or diverge together. If you can show the limit is a number which is neither 0 nor infinity. Take down some exercises. Integral 0 to pi by 2 sin x upon x root x dx. So, this you can try to do by comparison test 3, that is by showing an inequality f x is less than or equal to g x, or you can do it by limit also. Next, exercise 2, show that integral 0 to pi upon 2 sine of log of sin x, sine of better to use ln appearance, log of sin x is convergent, dx is convergent, that is integral 0 to pi by 2 sine of sin x times log of sin n x dx is convergent with value. So, you know the exact value here, log of 2 upon e. Next exercise, show that the improper integral 0 to pi upon 2 cos of mx upon x to the power n dx converges when n is less than 1, or like this also it may come, discuss the convergence of this integral. So, it will depend on n. So, basically you have to show let f x be this, which is less than or equal to some g x, which you have to work out, and then you will comment on n, for which value of n this integral will converge. So, you will see that it will converge for n less than 1. You will use comparison test 3. Next, we will go for absolute convergence, that is when your function changes sign within the interval. Up till now we have done functions which do not change sign. Now, we will come to functions which changes sign. So, we will see what will happen. So, here your function f x or integrand f x will change sign, changes sign within the range of integration. So, up till so far we have considered functions which are either positive or negative throughout the entire range of the integration. Now, we will come to the final case, that function changes sign within the range of integration, that is it becomes positive and negative. So, what will happen? So, the clever idea is that we will consider mod of f x. It is called absolute convergence. Mod of f x, because of the modulus sign, will become positive, and once it is positive you can apply all the comparison tests which have been taught, that is comparison 1, 2, 3, 4 depending on the kinds. So, what is absolute convergence? We will come to this topic now, which is the last topic of today's discussion. So, the absolute convergence of integrals. What do you mean by that? The improper integral definition, the improper integral integral f x dx, a to b f x dx is said to be absolutely convergent if we can show integral a to b mod of f x dx converges or is convergent, if it is possible to show. So, when we say absolute convergence, we mean that we will say our integral a to b f x dx convergent if we can show that its absolute value is actually convergent, that is integral a to b mod f x dx is convergent. If it is not so, that means convergent integral which is not absolutely convergent, which is not absolutely convergent, which is not absolutely convergent, is said to be conditionally convergent, is said to be conditionally convergent. It is a good practice to underline if we introduce something new. So, what it says that here integral a to b f x dx converges, but if we take the absolute value, that is integral a to b mod f x dx, it is not convergent. If it is the case, then we say it is conditionally convergent, and if the former one is the case, then we say it is absolutely convergent. So, now there is a very important theorem that if you can show an integral is absolutely convergent, then it is automatically convergent. So, whenever a function changes sign, so what we do? We just take its absolute value and try to see whether it is convergent or not. If it converges, then that means the integral a to b f x dx also converges. So, this is a very important theorem. You can try to look at the proof in the book. And absolutely convergent improper integral absolutely convergent improper integral is convergent. Very important theorem. That means it shows that if integral a to b mod f x dx converges, then integral a to b f x dx converges. Because you know improper integrals comes up or creeps up in many problems throughout science and engineering. So, it is very important to have a good idea of this. That is, if integral a to b mod f x dx converges, then integral a to b f x dx converges. But converse is not true. That means it is not true that if integral a to b f x dx converges, then its modulus also converges. It is not true in general. For example, I can give the example 0 to infinity sin x upon x dx. This is a very good example in this. So, we can show that this integral, that is 0 to infinity, see the range, sin x upon x dx is convergent, but if you take its absolute value, that is 0 to infinity mod of sin x, it is not. Then, but not absolutely. Okay. Let us do some problems in this direction. Exercise. Show that the improper integral integral 0 to 1 sine of 1 upon x to the power p dx. So, see, so it is the integral 0 to 1 sine upon 1 upon x by x to the power p. You can see this integral has a point of infinite discontinuity at x equal to 0. So, this converges absolutely for p less than 1. Okay. So, this is the problem. We have to show that this integral, if we take the absolute value, it converges for p less than 1. Solution. First of all, we have to observe that this integral changes sign. You can see sin 1 upon x from 0 to 1, it will change sign. So, the integrand, so first of all you have to investigate the integrand changes sign within the range of integration. Hence, we will consider the absolute value. Hence, we consider the absolute convergence of the given integral. What will happen if we consider the function f(x) equal to sine of 1 upon x upon x to the power p. This is the function. You can see it is a point of infinite discontinuity at x equal to 0. Has a point of infinite discontinuity, at x equal to 0. We have if I take now mod, so mod of f(x), that is the absolute value of f(x). So, this will become the absolute value of sine of 1 upon x, x to the power p, which is less than equal to 1 upon x to the power p, because x is within the range 0 to 1. So, this mod, because we know mod of sin x is less than or equal to 1. So, this will become 1 upon x to the power p, but we know that this integral will converge for p less than 1, since integral 0 to 1 dx upon x to the power p converges. Remember, we have done the p theorem for the second kind also, and 0 is the point of discontinuity at the lower limit. So, this integral converges for p less than 1. So, therefore, the given improper integral, that is this f(x), will also converge for p less than 1. The given improper integral converges absolutely for p less than 1, and because it converges absolutely, so you can just say it also converges. Take down some exercises. So, basically if your function changes sign, we take the absolute value, so that it becomes positive and we can apply all the tests. So, today we have discussed the comparison test. Take down few more exercise. Investigate the convergence of the integral integral 1 to infinity sin x upon x cube dx. As you can clearly see, the function changes sign between 1 to infinity sin x by x cube. Hence, we will consider the absolute value. So, if you consider the absolute value, so it is mod of sin x upon x cube, and so this will become less than equal to 1 by x cube mod of and because x is positive, so we can just take the, and now you know that by p series test, because it is 3 is greater than 1. Okay. So, this will converge, and hence this integral will converge absolutely. Take down another problem and we finish with this problem. Exercise, consider this integral minus infinity to infinity sin x upon 1 plus x square dx. Again you can see this function will change sign from minus infinity to infinity, hence you have to consider the absolute value. So, we take a mod of I, so it is mod of minus infinity to infinity sin x upon 1 plus x square dx, absolute value. And now you know that this will be less than equal to integral minus infinity to infinity mod of sin x upon 1 plus x square dx. And again now you can now break it up because it is minus infinity to infinity, so you can break it up. So minus infinity to some number c and then c to infinity. Okay, so this will be mod of sin x upon 1 plus x square, like this it will go on. So this will be I1 and I2, and now you have to check both the integral whether it will converge or not. If both the integral converges, then we will say it is convergent, and if one of the integral diverges, we say it will diverge. So it turns out that integral I1, it will be limit a goes to minus infinity integral a to c mod of sin x by 1 plus x square dx, and so it is turns out to be its value is less than equal to tan inverse of c plus pi by 2. Similarly, I2, if you work out, it will also be less than equal to pi by 2 minus tan inverse of c. So, if you add it up, we can show that hence mod of I is equal to I1 plus I2, which is less than equal to pi, and hence our given integral converges absolutely, and hence it is absolutely convergent. So, I stop here. Thank you everyone for listening. The topic improper integral.